Hello there. Today is the 15th of July and we're going to cover section 3 of chapter 13, which is thermal expansion of solids and liquids. So let's just summarize what we did so far. So we started with the concept of temperature, the idea of temperature. Then we talked about thermal equilibrium and the zeroth law of thermodynamics. Okay? Today what we're going to talk about, what is the effect of temperature in the length, in the size of solids and liquids. That's what we're going to talk today. Okay? So here you go. It's observed that don't forget, most substances, not all of them. It's observed that most substances expand their volume or their lengths, increase, here you go, let's put it this way, increase their lengths area and volume whenever their temperature increases. Remember, I said most, not all of them, okay? There are a few oddballs out there. That decrease their volume, that decrease their size with temperature. There are, but most of them should expand as temperature increases. I'm going to give you a demonstration of one type of substance that shrinks in size when you increase the temperature, okay? But for now, let's stick with those that are not the oddballs, the one that occur all the time. So what's going to happen? Let me show you a little illustration. We're going to start with the simplest of all solids, which is the rod. Can be a rod or can be a initially this rod has a initial length that we call L0. Okay, if we warm up this rod from its initial temperature to a final temperature T that's greater than T0, what's going to happen? It's going to increase its size a little bit. Okay, you don't always see something increasing its size. Sometimes a solid usually increases size by very little that you cannot see by naked eye. But that's the picture that you must have in your mind. You increase the temperature of a given solid and the solid is going to become longer. You start with and here we are talking about a one-dimensional solid, okay? To make our treatment simple. Then we're going to expand for solids that are not one-dimensional, but two-dimensional and three-dimensional. Okay, so consider the simplest of all solids. Okay, solids, one-dimensional solids. Solids such as a rod, a very long rod with a very small diameter compared to its length. Okay, we are going to model this. We're going to study what happened to a rod that can be treated as a one-dimensional solid, and then we're going to use this knowledge to expand to other solids that are two-dimensional and that are three-dimensional as well. Okay, so the rod in the book Here you go. That's gonna be, we're talking about figure 13.3. Figure 13.3 has an initial length L naught at a initial temperature T naught. Think about that. That's what we have there. The initial length are going to represent by the letter L, and the initial temperature I'm going to represent by the letter big T, T naught. Naught is usually used to represent initial. Then we increase its temperature to a value T. T that's greater than T naught. Greater than T naught. What we observe, as I said before, is that the length of the rod increases in size from L naught, okay, from L naught to a length L, to L, where L is, greater than L naught. Mathematically, we can write this new length as solid. Okay, mathematically we can write this new length as, here you go, L, new L equal to L naught plus a small change in the length that I'm going to call delta L. Here you go. That's how we start. Oh, and by the way, here is going to be L naught. Okay. Because there was an increase in the temperature, because the length of the rod increased because of temperature changes, we can also say that this length L is a function, okay, of the temperature T. It's a function of the genetic temperature T. Okay, so I'm going to write that as, something like that. L is a function of temperature T, which is equal to L naught plus delta L. That's a mathematical notation, right? Functional notation. L naught is a constant. L naught is a constant, and it's not a function of any temperature whatsoever. It's the initial length. So what's going to be a function of the temperature is this delta L here, is this change in length. So the functional dependence on temperature is right in here. It's right in here, okay? So L naught, the initial length, is not a function of temperature. Initial length is not a function of the temperature. Consequently, the dependency on temperature in the above equation must be in the term delta L. Or, here you go, delta L is equal to, it's going to be, a different function, not a function f, but it's going to be, I'm going to represent that by a different function g. Okay. What we observe is that within a relatively small ranges of temperature, okay, this functional dependence is linear. It's linearistic. Okay? That's the simplest dependence that I'm going to see out there, especially if the change in temperatures is very small. Especially. Okay? So here you go. So now what we so a good model, a very good model that we have, for the change in length of our rod, of our one-dimensional rod, is something like that, like the following. Here you go. Delta L is going to be given by a constant. Okay, here you go. I'm gonna denote this constant by the letter alpha, multiplied by the temperature difference with respect to the initial temperature. Temperature difference. And what else? We also find out that the longer the rod is, the greater the change in length we get. So it's not just alpha delta t, but it's also alpha delta t times L naught. See, we have a linear dependence on the temperature, and this term here is a constant. Okay, so our model, our theoretical model becomes, go back here, L equal to L naught plus alpha t minus t naught L naught. The length varies linearly with the temperature. Okay, so that's what you have to remember. And what else you have to know? Let us simplify the above equation. Let us simplify the above equation. Okay, I'm going to put L naught in evidence. I'm going to put L naught here in evidence. Here you go. That's another way of writing the same equation. Okay? So this term alpha that you see here, the multiplicative constant alpha that you see above, as you see above, comma, happens to have the following unit, 1 divided by Kelvin, right? Or 1 divided by degree C, right? Or 1 divided by degree Fahrenheit. That's the unit of alpha. If you want to make this equation dimensionally sound, this alpha must have a unit that's the inverse of the unit of temperature. So here you go, let's get that. Okay. There is one more thing about this multiplicative constant alpha. There is one more important thing about this constant. It depends only on the material that, let's see, not the material, the substance that the material is made of, that the solid is made of. Solid or liquid too, by the way, or liquid are made of. Because of that, we do have tables for the values of alpha for different substances. Okay, and this constant alpha we also call this constant. We also call here. Let's see. Let me get that. Is the coefficient, the linear coefficient of thermal expansion. So call the linear coefficient of thermal expansion. There are different values for this linear coefficient of linear expansion, and the values depend on the substance. Let's take a look. Here you go. We have different values for this coefficient of thermal expansion. Here you go. Glass brick, a special type of glass that's Pyrex. This other glass is Vicor, a different type of glass. Granite, most types of glasses, cement or concrete, iron, steel, copper, silver, brass, aluminum, and lead, and ice. Okay, and look what the values of this coefficient alpha, 10 to minus 6 for every degree C. Right? For, it's on the order of 10 to minus 6. The coefficient here increases as we go down. See that? It goes anywhere from 0.75 to 1 to 3.25, 8, 9.4, 12, blah, 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 until 51. Okay? It's a very small number. Okay, so when I told you that if I change the temperature of, let's say, this ruler, for instance, if I increase the temperature of this ruler, the ruler is going to expand, yes, it's going to expand. But the expansion is going to be very small. Let's come up with an example. Okay? Let's come up with an example so you can have an idea how much expansion you get out of a rod of all those materials, right? Let's start with glass Vicor. And I'm going to use my favorite software again. Here you go. And we're going to come up with an example right now. Here you go. Consider a rod, like a 1 meter long rod made of different materials. Here you go. Glass Vicor. Okay, with the lowest thermal expansion coefficient. I'm going to get a rod of iron. Another one lead, a rod of lead. Okay. And let's say we have a rod of ice, 1 meter long, at 0 degrees C. It goes with the temperature. And a rod and ice. So consider 1 meter long is approximately 3 feet of the following. Consider four different rods. Here you go. Let's do it this way. 4 different rods. Okay, each 1 meter long, made of the following different materials: glass Vicor, iron, lead, and ice. Okay, assume here you go. The temperature. Assume the temperature. Assume a 5-degree change in temperature of each of these rods. Find their final lengths. Assume a 5-degree increase in temperature of each of these rods. Find their final lengths. Okay, so here you go. I'm gonna do this solution here in my software. Here you go. Thermal expansion. Don't forget L equal to L naught, right? Plus alpha T minus T naught times L naught. That's the equation that you gotta know. The linear dependence. We must have this T minus T naught, okay? Because when T is exactly equal to T naught, the length is gonna be L naught, right? Note see that. So we must have this difference of T minus T naught, right? Here you go. Note see that at T equal to T naught, okay? L and O, cancel it. Well, be careful with that. T equal to T naught, L ends up being equal to L naught, right? So this equation is consistent. It's consistent with what we assume. But now we are going to do for 5 degrees difference. The temperature is going to increase by 5 degrees, which is 5 kelvins, by the way, right? And we are going to do for each of those materials. Okay, each of those substances. First, Vicor. Vicor, go back to our table, 0.75. 0.75 divided by 10 to the 6, okay? Degree Kelvin, just Kelvin. That's what we got for the alpha of Vicor. We use, that's what that means. That's what this thing means. This value, this alpha value is very small, by the way. It's so small that we can hardly see any change in the length of the solids. So here you go. By the way, we gotta put also L equal to 1, right? 1 meter. And we're going to use a change in temperature of 5 kelvins or 5 degrees C. We're going to use that. And then we're going to apply for each particular case. Oh, by the way, it's L naught here, not L. L naught equal to 1 meter. I'm going to substitute one L naught right in here. I'm going to substitute T minus T naught here. Okay. And now I'm going to apply alpha for each different material. Vicor first. Here you go. You know what was 1 meter becomes what? Becomes 1 plus 3.7 microns. That's how much the glass expand. This special type of glass expand. Let me see if I can put that in actual. Calculate. Yeah. Oh yeah. It's so small that he's not getting the numbers, right? So let's see. Let me put in a different format here. Collect. Oh yeah. Let's see here. I don't like the way he put it, but let's see. Expand, right? Let's try it one more. Let's see if you can get it. Oh yeah, here you go. And now the change is very small. The change in length is very small. Do you see that? So small that my calculator here doesn't even put the decimal places here in this number. Okay? So you can hardly see anything like that. It's 3 microns, okay? 3 microns is 3.7 microns. Think about that. What 3.7? Here is 1 meter. And here is 3.7 microns. 10 to minus 6 meters. 3,000ths of a millimeter. That's what it is. Okay, that's for Vicor. Let's do for the other ones. The next one is going to be which one? Which substance that's going to be? Iron, right? Here you go, iron. And all I have to do is to change the value of alpha. For iron is 12. Here you go. Okay, I gotta start. You know what? Yeah, too bad. Yeah, I'm gonna start here from scratch. Let's see. This one. Okay. And then what we get? You get 60 microns. A little bit longer, right? So here you go. Calculate it again. Let's see, let's just expand it. Calculate it. Yeah, that's what we get. 50,003 divided by 50,000. Let's see if you can calculate it. Yeah, 1.0001 meters. Okay? And that's because this one is larger than the other, right? Larger than this one. 10 times more than 10 times more. So this one that you see here is actually 1.000375. Around that. That's how small the expansion is. The next one is iron, lead. Let's go for lead now. Lead is 29. Lead. $29. It's going to be almost 3 times more than the other one. Almost 3 times more. So here you go. We do the substitution right in here. Here you go. Click and drag. Expand. Okay. Calculate. And here you go. What do you get? It's almost the same. Oh, 1, 2, 3. Yeah, it's almost the same. It's almost the same. What's happening here is that it is 1.00006. That's what this one is. Okay? So he rounded up this one here. It's not the same value, it's just slightly less. Just slightly less. And finally, ice water. Okay. For, here we go. See here. Ice water is going to be what? 51. Substitute again, right in here. Click and drag. And we can calculate. What do we get? It's going to be also around the same value that you saw. Yeah, oh, just a little bit more, 0.0003 meters. Okay. Almost 3 times more as this one. The change is almost 3 times more as this one. If you do that with your calculator, you might get a better answer. But that's what you get approximately. Let's see if I can increase the decimal places here. I don't think I can. Yeah, it doesn't look like I can. But you got an idea, right? It's 60 times 10 to minus 6 for iron. Here is 0.75 times 10 to minus 6, and so on. This one is twice as much as this one. This one is, almost twice as much as this one. Almost twice as much. So let's see if I can get the exact. I'm gonna copy this one. I think you can get more. Here you go. No, it doesn't. Funny. Let's try something else here. If I do this type of copy, maybe we can get more decimal places there. Let's see. Yeah, see that? Now I got it. So it's not exactly 1.0003. It's more like 1.00025, okay? So let's do that one by one. There's a little trick of this software. Let's see if I can get this one for Vicor. Vicor glass. Vicor. Yeah, see that? 0003. 1, 2, 3, 4, 5, 6. Okay? That's what we get for Vicor. This one here is for lead, okay? This one here is for lead. And this one here is for iron. Okay? So we increased from, look at the, I'm going to put every one below the other so you can see that more easily, okay? In a table format. Here you go. 1, 2, 3, 4, 5, right? Oh, wait a minute, not what I want. Insert 1, 2, 3, 4, 5, 2 columns. Substance. Final length. Okay. Substance Vicor. Iron. Lead, and the other one is ice water. So you can see the decimal places more easily. Here you go. Oh, by the way, meters. I don't need Right, here you go. We're just gonna put this guy right in here. Here you go. I don't need all those. It's too much. I'm gonna justify right. This one, oh. All of those are going to be justified right. So you can see the decimal places more easily. Okay, here you go. So what we get here, you get like that. 1, 2, 3. Okay, like that. I'm rounding it up. Lead, I got lead as well. Okay, so we gotta round it up as well. Here you go. We get 5, 0, 0, 1, 2, 3. Here you go. That's the final length. How much it changed? And let's get ice water. Let's take it down. Here you go. And becomes 500. Okay, that, oh, wait a minute, that's ice water. Lead must be different. Lead should be different, right? Yeah, lead is definitely different. Okay, like that. Iron. It's very small change, okay? 1 meter long, an iron bar that's 1 meter long, you have this very small, let's see, it's 6 microns. 1, 2, 3, 4, 5 is 60 microns. Okay, so that's 60 microns. 1, 2, 3, 4, 5, 6. Okay, for lead, we have a change. 1, 2, 3, 4, 5, 6, 145 microns. For ice water, we have 255 microns change. We don't see for 1 meter long iron by the naked eye. However, if you have a railroad track that is 1 kilometer long, 2 kilometers long, what's going to happen? Let's see. Okay, what happens to a piece of iron in a railroad track that is 1 kilometer long, 1,000 meters? Right? Let's see what happens. So all you gotta do is multiply this thing by 1,000. 1, 2, 3. And we get, you know, a 6 centimeters of difference. Okay, 1 kilometer long, a railroad track that's 1 kilometer long ends up stretching, you know, increasing in length by 6 centimeters. 6 centimeters is 2 inches. Okay, it's 2 inches. And it may make a huge difference. It may make a huge difference. I'm going to show you what, you know, for a railroad, in this case, okay, in this case, the track increases by 6 centimeters or 1,000.06 meters. It doesn't look like it makes a difference. It looks like it doesn't make a difference. But if you didn't design a railroad track properly, okay, it may affect it. But it does affect if you don't design your railroad track properly. Railroad track properly. Let me see. So let's check if your book has an example. Here you go. No, it doesn't look like he has it. Okay, I'm gonna show you in Wikipedia what happened. You know, people that didn't design the railroad track properly. Thermal expansion. Here you go. In Wikipedia we have. Okay. Oh, right in here. Okay. We cannot see. Okay, you can see clearly here. Look what happens if you have a very long bar of iron that was subjected to thermal expansion. The engineer didn't design this railroad track properly. And so what happened during a night, from the day to the night, because of the large variation in temperature, the iron tried to expand but couldn't expand because its two ends were fixed. Okay? And so what did the iron did? He went somewhere else. He went sideways. That's what they call buckling. Rail buckling. Okay? Thermal expansion of long continuous sections of rail tracks is the driving force for rail buckling. This phenomenon resulted in 190 train derailment during 1998 and 2002 in the US alone. Okay? So when you are designing something like that, you have to keep thermal expansion in mind. And there are ways to prevent that from happening. There are ways to prevent. Here we have another. Here you go. Let me see if we can get a better picture. No, we can't. Sorry. Let me see if we go back there. Yeah. This one. Yeah, instead of, it's strange. Instead of zoom in and zoom out. Okay. There is a little bit of buckling here too. Okay. Oh, this buckling here is terrible. See that? Oh, there's another buckling. See those little woods that they put across the track. Okay. So this phenomenon again that you see here is called buckling. The material tried to expand, but because its ends were fixed, it couldn't expand. So the only way that it would do it would be to buckle like that, flex. Okay, that's the only way it could go, because those two ends that are fixed are preventing the material from expanding. So how do they fix that? How do they fix this problem? How do engineers ensure that something like that doesn't happen to it doesn't happen just to railroad tracks, rail tracks. It also happens to bridges, okay? See a road bridge here? You have a slab of concrete. If you put just a single slab of concrete, it may try to expand, and just like the railroad, the rail track is gonna buckle, and then you're gonna crack your concrete. And you have to fix, to repair, or maybe you have even to demolish the bridge if it becomes too much damaged. But so in order to prevent thermal expansion from damaging the material, what do? They put what they call expansion joints. So you get one slab of concrete here and another slab of concrete to the right. And then they put a gap. They put a gap between those two slabs of concrete. Okay? And in this gap, they get this material here that leaves a little gap there for the concrete to expand and go back to its normal position. Okay? To avoid damage from thermal expansion. They do that to the rail tracks as well. Instead of getting a very long rail that may buckle with temperature changes, they get shorter lengths of rail and put a little gap between each rail. Let me see if they have a expansion joint. I don't think they have expansion joints here for the for the rails. Yeah, unfortunately they don't have. Let's see if I can find in the internet. Expansion joints. Expansion joints for rail tracks, for railway tracks. How does rail joint work? Let's take a look at this one here. Thermal expansion. Okay, why are gaps left behind between rail tracks? Let's look at this one here.
This is the checkers game where grandson and granddad will bond.
Topic: thermal expansion. Why are small gaps left in between rails? Don't know the answer? No worries. We shall find the solution.
Oh.
Okay, I don't want that. Let me see if I can skip that. I want to see an actual picture. Here you go. Oh yeah, okay, here you go. Must be right in here. Here's the buckling I'm talking about. What's the buckling? Here you go. There you go. The buckling. The difference here is that the buckling went upwards, right? But it can be sideways as well.
Do you think that the rails bent because of thermal expansion? If yes, then you are absolutely correct. A railway track is made up of a number
Here you go. Here's the joint, right? There is a little gap here between the rails.
of rails joined to each other. These rails are usually made up of steel. Steel expands on heating and contracts on cooling. When the rails are joined to one another without leaving any space for expansion, the rails bend due to thermal expansion and the train goes off the railway track. To avoid this, the rails are not joined together firmly. Instead, each rail is connected to the other in such a way that a small gap is left in between them. These small gaps provide space for easy expansion of the rails, which happens during summer, as well as due to continuous friction between the train wheels and the rails. Hence, these small gaps prevent the rails from bending, preventing any kind of accidents.
Okay, so that's the gap that they put there in the rails. Now we are going to move to another part of our class. Okay, so hang in there. Let's take a little break, and I'll be back shortly. I'm gonna pause this video so there's not too much of a gap when I come back, and we'll continue this material. Okay, we are back here, and let's continue. Here you go. The relation that we saw before, for the lengths of object, applies just to one-dimensional objects, right? Objects. Okay, what if the object has two dimensions? The object has 2 and 3 dimensions. What should we expect? What should we expect? Okay. Okay, let me show you. Let me come up with an illustration for you so you can understand how we should look at the case of a plate, for instance. Let's think in terms of a metal plate, very thin metal plate. I'm I'm going to get my illustration. Okay. My PowerPoint. Thermal expansion. Let's get thermal expansion here. Okay. So if we have a rod, like this one here, right? A temperature T0, we increase its temperature to T, and I'm going to exaggerate. And it's due to thermal expansion, the rod is going to get longer. Okay, but what if it's a plate? Here you go. A plate in which one of the dimensions is not negligible compared to the other one. In this case here you go. This dimension here is negligible compared to the length of the rod. So we can neglect any expansion that might happen along this direction, okay? But if you have a plate like that, then that you cannot, any expansion in the two dimensions cannot be neglected. So what's going to happen? How can you model something like that? Okay, the way you model is the following way. This plate is going to expand in this dimension, but it will also expand in this other dimension. That's how you should treat this problem. So if here we have a length A, okay, and a little bit larger, and in the vertical we have a length B. What's going to happen? The final length in the vertical direction is going to be B plus delta B, delta B, okay, gotta put here lowercase b, okay, here you go. Oh, hate that. Yeah, I hate when that happens. Keep on changing to capital B. And the other length is going to become A plus delta A. So it is as though this is a one-dimensional object that is expanding along its own direction. Okay, so here you go. I can put here outside now. This one goes a little bit more to the left. Okay, so here you go. And how do we treat this problem? Let me show you how we treat this problem. I'm going to do that again with my favorite software. Okay, two-dimensional expansion. Okay, here you go. That's one dimension, 1D expansion first, right? And then 2D expansion. Instead of using L, I'm going to use A and B. Okay? So the initial area is going to be given by A times B. The final area is going to be what? A plus delta A, okay? Multiply it by B plus delta B. And now you just use the same equation that you used before, but you're going to use in terms of A. And by the way, let's see here. Yeah, we keep A naught here. Don't forget, delta A is going to be given by this term here. Delta A, here you go. The initial length is A. I didn't put A naught there. I put A. The coefficient of thermal expansion is alpha as well. And we do the same for B. Okay, like that. The object is expanding in 2 dimensions. Along the x direction, along the y direction. Substitute delta A right in here. Substitute delta B right in here. And then what else do we do? Then we expand this equation. It's going to be a big thing here. But don't, and then I'm going to do something else. I'm going to call this guy here delta T to simplify my equation. Otherwise, it's going to become too large, too big to handle. So see that? Let's put this way. Here you go, delta T now. It's very important that we do this substitution right now. Otherwise, we are going to get a T minus T naught square here, and we're going to get a huge equation that's going to become difficult to manipulate. So let's use this one. I'm going to expand. Okay. So what do we have? We have my initial area right in here, right? See this term A, multiply it by this other term B. Then we get this second term here in terms of delta T, 2AB alpha. Okay? So where do we get that? We get from this term right here, A alpha delta T times B, A times B alpha delta T. That's what I get, this term here. Is this term crossed with this one. Okay? And this term here crossed with this one. And finally, we get our second order term in the temperature. Okay, it's a total of 4 terms that ended up being 3 because of that previous 2 terms. They sum up with one another. It's very important that we look here at this term. But let's do something else. Let's do something else. Notice that we have AB here, we have AB here, we have AB here, right? So we can go ahead and simplify. We can collect those terms, okay? We have AB. I'm going to call AB A naught. Here we go. And I'm going to rearrange this term. So we can have the number 1 before, so it becomes easier to visualize. Here you go. The term that's delta t raised to the 0 power, it doesn't show up. A term that's delta t raised to the 1st power, and a term that's delta t raised to the 2nd power. Not just delta t, but alpha as well, right? Here is alpha delta t to the 0 power, alpha delta t to the 1st power, and alpha delta t to the 2nd power. Very important. So what do we do next? Recall, recall that alpha, the coefficient of thermal expansion is very small. Remember that? It's very small. On the order of 10 to minus 6. 10 to minus 6. So if I square 10 to minus 6, like I have right here, I'm going to get 10 to minus 12. Have you thought about that? And 10 to minus 12 is very small compared to 10 to minus 6. Because of that, the 2nd order term can be neglected. I'm going to put that in my notes. Okay? So let me sort that out here first. Okay, here you go. Why did she pee there, Rico? Huh? Okay, don't pay attention to that. Here you go. And collect. Go back. So what I did here was to rearrange those equations in a better way. Right? So the term with the square can be neglected because the coefficient of thermal expansion is very small. Okay? So what can we do? We can, say that alpha square times delta t squared is approximately 0. Okay, but only the square term is negligible. They are not equal to 0. They are approximately 0. This term can be neglected, and we end up with this final relation for the area. Look what we get. It's very similar to the equation that we got before, right? Here you go. Let's get this one here in a different format. Recall what I had before here. Here you go. Collect. Here you go. Because I have delta t here, I'm going to write that as a delta t as well. Okay? I'm going to put my L side by side my area. Here you go. See that? LA 1 1 alpha alpha, but for A you have a 2 alpha here. Delta t, A naught, L naught. Don't forget what we have here is an approximation, not an equality. This coefficient that we see here we call coefficient of surface expansion. Here's the coefficient of linear expansion. Here's the coefficient of surface expansion. Okay, I'm going to copy this one to my notes so you can have that documented. Here you go, step by step for you. For 3 dimensions, we have a similar derivation. For 3 dimensions. Huh. For 3 dimensions, for 3-dimensional object, we have a similar derivation. Let's do that together. Okay. So, first, let's visualize it. Our 3-dimensional object. Here you go. Here my 3-dimensional object. Okay. Just like before, this object is going to expand along this direction. It's going to expand along this direction, right? And it's going to expand along the other direction as well. Let's try it again. I don't like that. Here you go. They have exactly the same dimensions right now. Let's see. Should expand only in this direction for now, right? The only change is in the vertical. Okay? Then we're going to expand this object along the horizontal. Yeah, but he's contracting. Let's see here. Yeah, I shouldn't. Too bad. But that's okay. Yeah, it doesn't look like I can do anything about that. Okay, so now my object expanded in every possible. Let's go a little bit here. Here you go. Okay, expanded this direction, expanded in this direction, and then should be thicker as well. Okay? We apply exactly the same reasoning that we got before. We have this one is A, let's say this one is B, and this one here is C. This one here is C. Okay? What else? We have A plus delta A. We have B plus delta B. And then we have C plus delta C. And you do the math all over again, like we did before. 2D, 3D expansion. 3D expansion, here you go. 3D expansion. Now we're going to call volume. Initial volume is A times B times C. Final volume is going to be A plus delta A times B plus delta B times C plus delta C. Okay? each of those 3 dimensions, they expand in the same way that we saw before. Here you go. The materials are exactly the same along the 3 directions. Okay. And I have my equation here. Let's. I'm going to hide this thing here. I gotta delete the rest. Okay. Now this one. My delta t goes here. I don't need that. I'm going to substitute delta A. I'm going to substitute delta B. I'm going to substitute delta C. And T minus T naught, I'm going to substitute by delta T. We are going to rearrange those equations, this equation here. So we have the terms without the delta T as being the first one, right? I can, here you go, I can collect them. I'm going to simplify, here you go, ABC, okay, here you go. This term ABC is V naught. Okay. And now we go ahead and expand this term. It's the cube, right? The cube of 1 plus alpha delta t. Let's do it. Here you go. Expand. You should know how to do that. And I'm going to put the number 1 first. Oops. The linear term second, the square term third, and the cubic term last. And now we apply that approximation that we used before. Here you go. The terms with the square and cube can be neglected because the coefficient of thermal expansion is very small, on the order of 10 to minus 6. So what we're going to do? We're going to do that approximation that we did before, but now for the a square and the alpha square t delta t square and alpha cube delta t cube. Okay? Alpha cube delta t cube is even smaller than alpha square delta t square. Here you go. Next. Okay? And look at the relation that we get. Very similar to what we got before. Here you go. L is 1 plus alpha delta t. A is 1 plus 2 alpha delta t. V is 1 plus 3 alpha delta t. Okay? Exactly the same procedure with a slightly different result. Okay, so here we go, like that. I don't need that. Here we go. I'm going to erase that. So here we go. I'm going to just put here. Here is my final result, showing explicitly the approximation. Here's an equality, right? But we have an approximation. Let's see how your book does that. Area expansion, here you go, 2 alpha. And volumetric expansion, 3 alpha. Liquids, you know, they occupy a volume, gasoline, water, mercury. That's why we need the volumetric expansion coefficient. Liquids and gases, right? So applications to thermometers. Okay, so we have the mercury thermometer, we have the alcohol thermometer as well, the alcohol in a glass. So as the temperature increases, the alcohol inside the glass expands as well. And we usually put a dye to give color, a little paint dissolved in the alcohol to give color to the alcohol, so you can see more clearly the column of alcohol. That's what we have here, right? And basically that's what we have for thermal expansion. I'm going to save those notes. Okay, and I will post, eventually I'm going to post there in the website, okay? So let's take another break, 1 hour and a half.